All right, so I'm going to look at you guys once, and I'm going to take my glasses off because I can either see you or my computer. And I've been drinking coffee for like 10 hours straight, so if I start talking too fast, just go like that, okay? Okay, so my name's Rob. I'm from Portland, Oregon. This is my first time in Montreal. It's cool. For my day job, I write software for big telescopes in Scala. But I also work on some open source projects, sort of to help promote and support programming with types in a pure functional style in Scala. So if that's the kind of programming that you're interested in, I encourage you to get involved with type level. I have a sticker here. Because that's what we're all about. So it's a cool organization if you're interested in functional programming in Scala. I would have put the logo up here, but I can't understand CSS. If you don't mind admitting it, how many people here have used Scala Z, or CATS, one or the other? Okay, so maybe a third or half. So that's more than I expected. Okay, so today I kind of just want to talk about some odds and ends that I think are interesting, and we'll see if you find them interesting as well. So here are the goals. The big thing I want to do is help you get an intuition for some simple recursive types. These things seem to be pretty well known in the Haskell community, but not that much in Scala. I think they're interesting and useful, and it's just a fun thing to learn about. And then gain some confidence pushing code around and pushing on it. And this is something that I mention from time to time when I give talks, and people are always like, can you say a little bit more about that? So I'm going to try and give some examples of that, and you'll see what I'm talking about. So learn how boring Doobie is. Doobie is a database library that I work on, but it's a pure functional database library. It's side effect free. Using it in a pure style is very uneventful. It's not really actually all that interesting. It just kind of works. So this is ostensibly a talk about database programming, but it's kind of going to be an incidental thing. Okay, and don't panic. So recursion is always kind of mind-blowing when you first started learning functional programming, or if you are doing that now, learning about recursive functions, self-referential data structures, that sort of thing. It's hard. And today we're going to talk about self-referential types. So just be seated, remain calm, and I'm going to try and go really slow and introduce this very gradually, hopefully in what's going to be a natural way to see how these ideas pop out. So it may be too slow for some of you or too fast for others. It's hard to thread that needle. So if you get lost or have a question, please stop me so we can all stay together. All right, so let's look at a recursive data type. Okay, so here we have a data type for professors and their PhD students. So we have a case class. We've got a name, the year that person got their PhD. That's what the year is. And their students, which is a list of other professors, right? So it's a self-referential structure. And I have an example of what that structure looks like. Okay, so imagine there are lines connecting those boxes. So we have Hilbert, who has 3 students, and then Weil, who has 1, and then MacLean, who has 2, okay? So it's just a tree structure. And that's the kind of thing you could represent with this case class. Does that make sense? Okay. All right, so the kind of invented problem I want to talk about is how do we take a structure like this and save it to a database and then load it back? That's it. A very simple problem that has a lot of interesting consequences when you think about it. Okay, so this is normally the way you would represent this kind of a structure in a relational database. You have a table, it's got a unique identifier for the professor, and it's got a possibly null link to the parent. If you're at the top, if you're a Poisson, you have nobody above you. Otherwise, you have some parent. And then the name and the year, and then there's a foreign key, so the parent refers back to the table. So So the difference is the relationship is inverted. The natural way to represent it in Scala is not the same as the natural way to represent it in a relational database. So we're going to talk about that relationship and how to manage that in a little bit. But the first thing I want to do is talk about just how we represent the ID, because that's an interesting problem. Okay, so here's one way to do it. So we have a new field, an ID, which is an int tagged with prof. And I'm not, if you don't understand what that means, it doesn't really matter. You could use an any-val or a case class or something just to make it a distinct type. For simplicity, I'm just going to use a plain int. Okay? And I'm going to get rid of the table because we don't need to see it anymore for a while. Okay, so we have this. So we have a professor. We have an ID that's an int and all those other fields. So what is wrong with this representation of the database ID? Very good. What do we do with new objects? When we construct one, we have to have a special value that means this doesn't have an ID yet, right? So that's no good. This is Scala, so we want something in the type that will tell us whether it has an ID or not, right? We don't want to have magic numbers, right? Okay, so what about this? Is this any better? So now we have an optional ID. So it's a little better, but I think it's irritating. So really we have three cases to think about. Either it's new, you just constructed it so that you know there's not an ID, right? Or you just got it from the database, so you know there is an ID. Or you're doing some computation on them that doesn't care whether there's an ID or not. But you have this extra field you have to deal with when you're pattern matching and that sort of thing. So it's irritating in all three of those situations. So one way to make this kind of less invasive is to externalize the ID. So we can do something like this. So we can go back to the original definition of prof and then have a type alias. An ID prof is a pair of an ID and the model object. Okay? The problem here, of course, is that the children need to have IDs too, right? So now we put the ID back into the model type, which we were trying not to do. So that's no good. So let's try something else. What if we just have a type parameter and we parameterize the child type? So let's do that. So the data type is not recursive anymore. We just have a type parameter, and then we have a list of whatever the type argument is as the children. So, and then we can have type aliases. We can say a prof is a prof f, and its children are also prof f's, right? An ID prof is a pair of an int and prof f's whose children are pairs of ints and prof f's, right? So let me note that I've renamed this type prof f just to distinguish it from our original data type. Okay, so does this work? Will this compile? No. This will not compile because prof f, the type argument here, also needs a type argument, right? So this is what you end up with, right? So it doesn't work because the types are infinite. So you can't do it this way. All right. So what if the type aliases are self-referential? What if we do this? So type prof is prof f of prof, which is what we're defining, right? And so you expand that, and that's prof f of prof of prof, forever. So you tie the knot that way. And does that work, Daniel? No. No, it doesn't work. Because type aliases can't be self-referential in Scala. Okay? But classes can be. So what if we do this? Does this work? This does work. This compiles. So we have a case class called prof, and its value is a prof f that has more profs in it. And that actually works. So this is cool. We have one representation of the model object, and depending on how we wrap it, it can either represent just sort of the naive tree structure, or a tree structure where each node is annotated with a database ID. So we get both of those representations with the same basic model class, which is pretty cool. So we could claim victory at this point and just implement this, and this would work. But this is functional programming, and we like to generalize things. So let's push on these data types a little bit more and see where we get. So something to note about prof and ID prof is that there's nothing in those implementations that's specific to prof f. We're not referring to any of the fields in the data structure. So we can just factor it out. Okay? It's just turned into a type parameter. So instead of prof f, we just have any f with one type hole in it. And this doesn't compile because now prof it needs a type argument. We're just calling the type constructor recursively, so we just need to pass f there. Okay? Okay, getting some stares. Okay. So, let's also note that there's nothing in ID prof that depends on int. So let's turn that into a type parameter as well. Okay, so now what do we have? We have two recursive types that are completely generic, right? The first one can make any f recursive, and the second one can make any f recursive and also annotate each one with some other value, with some out-of-band sort of value, okay? And it turns out that these are both well-known types. So the first one is called fix, and the second one is called Cofree, and they do exactly what we've been talking about. I will mention, so Cofree is sometimes called the Cofree comonad. It's the categorical dual of the free monad, which everybody's been talking about for years now if you've been to Scala conferences. Okay, so just very quickly, Cofree is an A and an F of Cofree of FA. And the free monad is an A or an F of free of FA. So it's just the difference whether you have both of them or one or the other. And that's how these types are related. Okay? And that's where the name comes from. The co is, in category theory, you put co in front of things to get the dual. Okay. And I should also say that Cofree and free are both special cases of fix, and I think Greg Feil, who's coming up next, is going to have something to say about that. Okay, but this kind of illustrates what I'm talking about, pushing on code, because if you push hard enough, sometimes it just disappears entirely, because anything I invent that is sufficiently polymorphic and plausibly useful probably already exists in Scala Z. In this case, that's half true. Cofree is there, and also in cats. But neither of them has fix for some reason. I don't know why. Okay. So now that we kind of know about the general types, we can define prof and prof f trivially like this. So we have a type alias for prof, which is just fix of prof f, and ID prof, which is the Cofree annotated with an int. Okay, so I may have lost some people at this point, so I want to come back down to reality and just do some things with these types so you can see that they're not frightening. Okay, so here's our original recursive data type. This is what was on slide 2. And this is a construction, okay? And there's nothing fancy about it. So we've got Hilbert and his students, and so actually there's something pretty awesome about this. So both Curry and Howard from the Curry-Howard correspondence are in here. Wilhelm Ackermann from the Ackermann function. And Saunders MacLean was a professor for so long that both Howard and Steve Audi got their PhDs from him 41 years apart, which is pretty amazing to me. Okay, so anyway, so here's how we would do it with fix, okay? It's exactly the same shape, right? The only difference is each prof f that we construct is wrapped with a fixed constructor. That's the only difference, same shape, okay? Cofree, same thing. It's wrapped with a Cofree with an annotation attached to it. But that's it, right? So even though the types here are a little challenging to wrap your head around at first, they're just, and the names are kind of intimidating, but they're just data. You can construct them, you can pattern match them, you can write functions that deal with them. It's not scary. You may have to take my word for it. Okay. So before we get back to the database problem, I want to show you an example of programming with these types in a completely pure environment, so we don't have to worry about I/O effects, because that's going to make it a little more complicated when we get back to the database stuff. So we're going to write some parsers. Okay, can we read that? Yeah. Okay, so here is a big multi-line string that has a bunch of mathematicians and the nesting is indicated by indentation. And what we want to do is parse this into our fixed point types. So here's one way to do it. This is a parser that's written in Atto, which is a parser combinator library that I work on, but it would look the same in any monadic parsing library. It would have the same structure. So what does this do? It takes an n, which is the indentation that we're looking for, and it says, okay, so we're going to skip the indentation, we're going to read the string up to the comma, then skip the comma and the input after it, read an int, skip the new line at the end, and then the magic part is we're going to call ourselves recursively at a greater indentation and read anything we find at that indentation. And then at this point we have the name, we have the year, and we have the list of students. So we have enough to construct our fix of prof f, which we do, and that works. So we say, okay, we want to parse starting with 0 indentation. We only want to parse the data, that there's no more input following it. See the result as an option, and we get something with a terrible toString. But if I call this utility method that I'm not going to show you, it's in the sample code, we can see that it parsed out correctly. It has the right indentation. Okay, that was no harder than just parsing a regular flat recursive data type. There's really nothing more to it. So let's see what we can do with Cofree. So here's our fixed parser, and here's one with Cofree. The only difference is the first couple lines and the last couple lines. So what we're doing here is we're associating each thing we read with the position in the input text. Okay, so before we parse anything, we get the current offset position, and then when we're done, we get the current offset position. Then we construct a Cofree with that pair of ints associated with it. Okay, and it works again with a terrible toString, but if I draw it out, that's what you get. So you get this tree structure, and then each node has the parse positions associated with it, which I think is pretty cool. So our original idea was to use this Cofree structure for database IDs, which is great, but we can also use it for parse positions. We can use that empty slot for anything we want. And we did this without changing our model representation. It's still the same prof f we had on slide 3 or whatever. And you might see how this can be really useful for something like a programming language, right? Where your recursive, or your data type is some AST that's self-referential, and if you use Cofree for that, then you can annotate it with source positions and types and whatever, strictness analysis, any number of things. And you can do this without ever having to modify your AST. This is something that can happen off to the side, which is really cool. Okay, so let's get back to the database problem. But before we can do that, I need to explain something else that you might have been wondering about, which is why the f in prof f. So prof f is a functor, which means we can map over it. And if you follow this design pattern that I'm talking about, it's always going to be a functor. And this pattern is called pattern functors. I don't know where the name comes from, but if you're interested in this kind of programming, Google pattern functors, and that's what this kind of thing is called. And you'll find a lot of stuff out there, mostly in Haskell, but there is stuff out there. So how do we do that? How do we implement functor? Well, the A here only appears in students, which is a list. List is already a functor, so we already know how to map over list. So basically, our implementation just delegates to map on list, and it copies the structure. So if we see at the bottom, if we construct a prof f of string, and then we map it, we can get a prof f of int back, right? Prof f of string doesn't really mean anything useful, but it demonstrates that the map operation now works. Okay, does everybody follow that, kind of? Okay. All right, so, but there's more. It turns out that prof f is a traversable functor, which means we can sequence over it, which is going to end up being very important. So let's skip the implementation and look at the sample down at the bottom and just look at the types, okay? So the first thing we have is a prof f of option int. After we call sequence, we have an option of prof f of int. It flips the two type constructors around. Okay? And that's the magic trick that you get with traversable functors. It lets you do that. The first one has to be a traversable functor, and the second one has to be an applicative functor. And then, again, if you look at the implementation, it's a little more involved, but list is already a traversable functor, so ultimately we're just delegating to the implementation on list. Okay, so if you're doing monadic programming, traversable functors are really going to help you. So if you don't know about them, it's worth studying because they will make your life much easier. A lot of people start doing, playing around with pure functional programming, a lot of monadic programming, and just tie themselves in knots because they don't know how to do this trick where you flip the type constructors around. So it's important to know. And another little digression about that. Very, very commonly we'll map something and then want to sequence it. So we'll map it to construct this thing, but the type arguments are in the wrong order, or the type constructors are in the wrong order and we want to flip them. So we define an operation called traverse that's the same thing as mapf and then sequence. And I say they're the same thing, and what I mean is they're the same thing. You can do a syntactic substitution of one for the other without changing the meaning of your program. And then using that, we can find another identity that's useful. So the functor law tells us that FA and FA map identity are the same thing. You can take any functor and replace it with whatever it is, map identity, and it won't change the behavior of your program. Therefore, FA.sequence is the same thing as FA map identity.sequence. But FA map identity.sequence is FA traverse identity, right? So just by pushing these formulas around, we get the identity that FA.sequence is the same as traverse identity. Okay, so if you're working with this stuff, it's useful to know those two substitutions because you'll end up using them. Okay, it's kind of trivial, the example, but people will ask, what kinds of things can you do? What does equational reasoning mean? And it's just a very little example of the kind of thing you can do. And we'll use this in a little bit. And you've all been wanting to do some SQL, so let's do that. Okay, so I don't have time to talk about Doobie in a lot of depth. It's a pure functional JDBC library that I write. Side effect free. Everything is referentially transparent. And the big idea is that Doobie programs are values. They are data. They don't do anything until you translate them into some target monad like IO or task that actually has a runtime meaning and is actually capable of executing this program that will go out and connect to the database and do stuff. So here we have an example. So for the things in the talk, I'm using an in-memory database, and this first thing is a transactor, which is just abstracts over connection pools. That's basically all it does, and it fixes the effect type, in this case to Scala's effect IO. So we construct that, and then create is a program that will create the schema. So we have a SQL literal, we want to interpret it as an update, and the run method it doesn't actually do anything. It just transforms this sort of query builder into a connection IO. In functional programming, for some reason, if we can't think of a name for a function, we call it run, and they're all over the place in Scala and it's in Haskell, and so it's just unfortunate. So don't misinterpret it as actually performing any IO. Okay, so down at the bottom in the REPL, we're going to initialize the database. So we can say, we'll get this create program, we will associate it with the transactor and say, do this thing on a connection in a transaction. And that gives us an IO, in this case an IO of int, and then we can unsafe perform IO to actually go out and do something against the database. And it returns 0 because there were no rows modified. In the second statement, just as an example, we can say, okay, I have the SQL literal, I want to treat it as a query that yields ints. I want to gather them as a list, and then do it as a transaction and unsafe perform IO, and get an empty list because the table's empty, of course. So that's really all you need to know about Doobie to follow the rest of the talk. If you're interested in pure functional database programming, if you go to the repo, There's what I think is a pretty good doc. There's a presentation that I gave at Scala by the Bay last year that kind of explains how everything fits together. Okay, so let's insert a tree into the database. So here's a method, and this method takes an optional parent ID, because the root is not going to have a parent, and it takes a proff of anything. So it constructs a program that inserts a row into the prof table and yields the generated ID. Okay, so we want to SQL literal. We're going to interpolate these arguments. The optional one will get turned into a null if it's none. We want to treat it as an update, and we want to pull back the generated key called ID from the ID column. So we end up with a program that describes how to go out to the database and insert something and get an int back. So all it's doing is inserting the parent and the name and the year. It's disregarding the children altogether. And you can tell that just by looking at the type, right? It's an existential type. So the implementation has no way to know what kind of values are in the students list. So you can tell just from the type that it can't possibly do anything with the children. And here is a method that constructs a program to insert a fix of proff, which is the unannotated tree. Oh, yeah, Daniel, I'm sorry.
I mean, the children are a list, so you still could do things with children, like
you could count them.
Yeah, you can count the children.
Yeah, yes, you could count them. Thank you.
I was thinking about it, it's like why use the existential type rather than using like nothing or something like that? I mean,
yeah, okay. Let's just well. Proff is invariant, so you would have to, and the idea is you should be able to pass. You should be able to pass anything. The implementation doesn't care, so yeah. I mean, you could argue it either way. It's just kind of a throwaway thing. So, okay. So insert tree takes a fix of proff, which is the unannotated tree. And then it takes an optional ID for the parent of the root of that tree. And what it gives you back is a connection IO, right? So that's a program that might interact with the database. And what it computes is a Cofree, a proff event. So it's going to, what it's going to do is it's going to take a tree and it's going to give us back another tree, but every node is going to be annotated with the generated ID from the database. So how does it work? So the first thing we get a fix of proff, and the only thing we know how to do with it is insert node. So we'll call insert node, and we get back a connection IO event, and that gives us the ID back. That's our head. That's going to be the head of the Cofree. And for the tail, we get the proff, and we map recursively. We call ourselves recursively, and for each child, we insert that tree. And look at the type that's next to the insert tree line. The type is a proff of connection IO of Cofree. So what is that? That is a proff whose children are programs that insert each of the subtrees, which isn't what we want. So we call sequence, and what we get back is a program that computes the annotated tree. That's why we had to implement the traversableFunctor here, so we could do that trick. So we learned that map followed by sequence is just traverse, so we can simplify that a little bit. Okay, and insert tree can be generalized a little bit, but I'm not going to go through that exercise. The option kind of makes it difficult. Okay, does it work? Well, yes, it works. So here's an example. We parse the fix version the way we did before, and then we construct a program to insert it. And then we pass the result to this IO draw Cofree routine, which is just a version of that same method that works in IO. And then when we unsafe perform IO, this thing, it goes out to the database and it inserts everything. And because of the way we define the traversal, they all come back numbered in order top to down. It's a little suspicious that they start at 1, so I did it again, and now they start at 20. So it really is using the sequence from the database to assign these IDs. I should mention this entire talk is a REPL session that's type checked and run, and there's a tool called Tut that does this that's useful when you have a presentation or something that has a lot of code in it. Okay, so how do we read this tree back? So here is a method that constructs a program that goes out to the database and it does something, and it computes a proff of int. Now, what does proff of int mean in this context? So it's a proff whose children are database IDs. Okay? So we've used this same structure for a lot of things, and this time we're saying instead of having a recursive structure that's this tree with object references, we have database references, which is kind of cool because a lot of the time when you're writing a database program, you might want to deserialize this whole object graph, or you might just want this local thing with database IDs pointing out. And you can get that from the same representation this way. Yes?
This will be just one level, right?
This will just be one level. However, if you said proff of int, then you get 2 levels, and then you get ints, or proff of int, and you get 3 levels, right? Because each time you go down into the students, it peels one of them off, right? So, which I think is a really cool thing. That's a great question. I was going to mention that anyway. You can load back something in the middle of a graph from the database, and you can say, I want to be able to, take some number of steps out from it before I have to go back to the database. And this lets you represent it in the types. If you've ever used Hibernate, like back in the Stone Age, it lazily loads stuff as you traverse, which is just ridiculous, and you get all these lazy loading exceptions and stuff. And this hammers it down into the types, which is really nice. So it's a nice consequence of this encoding that you get all this flexibility in the way you use this model object. So I will acknowledge that this way of doing it is very inefficient. I'm doing 2 selects for every node that we read back. Of course, you can do it in a much more efficient way, but this is more clear just for demonstration purposes. This makes it a little bit easier to follow, so I'm going to leave it this way. So what we're doing is we are selecting a string and an int, and this, at the end, it's unique, which says we expect exactly 1 row back. So we get a hunk of data that has these 2 fields in it. And then we're selecting a list of all the IDs of the children. And then we're putting them together to construct a proff. Okay, so now we can read a slice with database references, and how do we put this together to build a tree? So we do this. Okay. Let's follow the types, shall we? We have an ID that's given to us, and what we want to read back is a connection IO of Cofree of proff of int, which is a proff tree annotated with database IDs. This is what we've been working with. So we have an ID. What do we know? What can we do with an ID? The only thing we know how to do with an ID is called read node. So we'll do that, and we get a connection IO, and we want to return a connection IO, so we're going to flat map. So PI, that's a proff of int. So if we map that recursively to read tree, we get a proff of connection IO of Cofree proff of int. So, which again is the proff with the leaves annotated with programs that read the trees back, which is backwards from what we want, so we call sequence. And then we have the 2 pieces now that we need to build the Cofree. We have the ID, which was provided to us, and we have the proff with all the children. So we have to use map there to do it, but we construct the Cofree, and that's it, and that works. So we know that map followed by sequence is traverse, so we can simplify that a little bit. Okay. So I'd like to take a minute and look at this read tree method a little more closely and see what we can do with it. So the first thing I want to do is factor out the call to read node. So now we can take any f that goes from int to connection IO of proff of int. Okay, all we did was just remove that call and pass in the function of that shape. Okay, so what does this do? So f gives us a connection IO, and the only thing we ever do with it is we call flat map, and then later on we call map with it, right? So we don't need a connection IO. That's too specific. We can use any monad. So let's factor that out. Okay, so now we have an int to m of proff of ID. Well, what do we do with the proff of ID? The only thing we do is call traverse on it, right? So we can take any traversable functor there. We can factor that out. And of course, we're not doing anything with the int other than passing it to methods, so we can factor that out. Okay? So what we're dealing with here is it's a useful thing. It's completely generic. So this is a monadic Cofree co-recursion. It's an unfold. It takes a seed value and it feeds it into a function that generates this f in some context. And then it traverses and expands all the a's within it forever until it gets to the end, until it gets to the leaves. And what it gets back is a Cofree that's annotated with all the leaf values that have been generated. So does this already exist in Scala Z? It doesn't, actually. I was surprised. The non-monadic version of it does, and it's called unfold C. And this is just one that does this in a monadic context. So it's an oversight in Scala Z. So in any case, with this method, no, I wasn't kidding. It totally should be in Scala Z. It's just nobody has, whatever reason, nobody's run into it before. In any case, once we have this method, read tree is trivial, right? It's just, we're just delegating to unfold CM. So I want to point out that doing this kind of thing is worthwhile even if you only call it once. The more polymorphic your code is, the fewer ways there are to write it, which means the fewer ways there are to write it wrong. Okay, so sometimes there's only one way to write it, and if it type checks, it has to be correct, which is really cool. It's not the case here. There are a couple ways to do it, but far fewer than there would be dealing with concrete types. So does it work? It does, in fact, work. So we're going to read Hilbert, who's 32, and then print out the Cofree, and there it is. Came right back. So I think it's really cool that we're using this totally generic monadic unfold to do this database operation. And we never thought about, what are we going to do with the connection and the result set, and we got to iterate and do it. Because this is functional programming and we're using lawful type classes, it basically just has to work. We're just going where the types lead us. And lo and behold, it actually does what we expect. Okay, so what have we seen? We learned about some recursive data types, and what I want to point out is Fix and Cofree popped out of what we were doing very naturally. This isn't like some obscure theoretical thing. It's actually useful, and dealing with database IDs is something we actually have to think about. So it's not a contrived example. We used them to do something useful. You saw all the different ways we were able to represent, all the different things we were able to represent with the same model definition. All these different representations with and without keys and with database references and object references. And we pushed our code around, and hopefully even if you didn't follow all this, that gave you some idea about how we can think about things when we're doing functional programming with types, and some of the power that it gives you for reasoning about your code. And hopefully you survived. I know these ideas are kind of challenging. I have bad news for you because my last slide here is this slide probably right here is the first slide of Greg File's presentation, which is coming up. So he's gonna take this a lot further. And that's it. Thank you.